All right, so this is Group 25 presentation on Z transform. So how will we introduce Z transform? So we're going to compare and contrast with what we know. And what we know is the big three for continuous signals, which is Fourier series, Fourier transform, and Laplace transform. So say we have the sinusoidal signal, which is periodic, and we put it through the Fourier series. We get these two impulses at -1 and 1. The height is 1/2. So if we get a non-periodic function, which is an impulse, and we put it through the Fourier transform, we get a magnitude graph that is a sinc function, which doesn't repeat. Both of these don't repeat. They end where they need to end. So this one goes to infinity. This one stops at 1 and -1. And Laplace transform is something we haven't really talked about much in 327, but utilized a lot in 343 and 375. It's a great thing to look at when we're talking about Z transform. It helps it to simplify a bit more if you're familiarized with Laplace transform. So say we have this exponential signal and we send it to the Laplace transform, we get this graph. We haven't really looked at the graph when using Laplace transform. Like if you in 343, we just did the equation and we went back to time domain. So it's just something that's not useful in that situation. But in this, we're looking at Z transform. And so it's very useful to look at it and compare to the Z transform graph. So the big three for discrete signal. So whatever you can do to a continuous signal, you should be able to do to a discrete signal. So two of those three is the discrete time Fourier series and the discrete time Fourier transform. So say you have that sampled sinusoidal function and we put it through the Fourier series, we get two impulses. This may look like it's the same, but however, it actually repeats on every 2 pi. So 0, so 2 pi, two impulses. -2 pi, two impulses. So it's not the same, but it has the same function that's repeating. So now we have a sampled pulse, not periodic, so we put it through the Fourier transform. We get a repeating sinc function, just like this. Same function, but it's repeating every 2 pi. So this would be 0, this will be 2 pi, this will be -2 pi. So what's the third one? Well, we don't know, which is actually Z transform though. So what is Z transform? So Z transform is converting a difference equation to an algebraic equation by moving to the Z domain, making life a lot easier. So if you look at Laplace, we used it in 343 for a reason, because we're looking at RLC circuits. RLC circuits have differential components to it. And we move to the S domain, so we get algebraic equations, which are easy to manipulate, easy to solve, and then go back to the time domain, and we have an easy function to get to in the time domain, right? So like it makes your life a lot easier. You don't have to do any differential analysis. It's just algebraic analysis. So same thing for Z domain. It's equivalent to a Laplace transform, but you don't get differential equations in the discrete signal. You get difference equations. And Z transform simplifies the calculations of finding the discrete time Fourier transform if it exists. Z transform also allows you to see if it exists. More on that in the rest of the video. So this is a difference equation, right? These come from LTI systems. It's just the signal is time shifted. It may not look hard, but if you have a complex signal, it gets complicated because you have to add up that signal time shifted. And you can only really do that graphically, but if you put it into the Z domain, it just becomes a rational function after manipulation. And we know how to solve this by using partial decomposition. All right, so Z transform equation and notation. So equations used to convert from time domain to Z domain. So consider we have this signal and we have the general equation of getting to the Z domain. So what is this general equation? So this signal is the signal we're considering here, and Z to the power of -n is the transform basis function. So it's what allows the transform to the Z domain after summing it up from -infinity to infinity, right? So, and then the x of z is a S domain spectrum so that you can get the phase spectrum, you can get the magnitude spectrum, and you can get the imaginary versus real graph. And then the notation is very similar to the Laplace notation. It's a z instead of an L. And one thing that's very important is that z is a complex variable. So important characteristic of the Z transform equation. So the summation equation can act as a geometric equation. So let's take our attention back to that general equation. So we have a power of -n. So that gives us freedom to use a geometric series equation if xn allows us to. So a quick example would be, let's say xn is a casual exponential. So we put that into the general equation, we get this, right? And we know the geometric series equation identity. So the identity is right here. So if b to the power of k, if we have that, then that should equal 1 divided by 1 minus b, right? So if we have the identity, we can manipulate this equation and have it identical to this one. Also, k is equal to 0 to infinity. So the summation is happening from 0 to infinity, which is where the unit step comes from. So we take the unit step, go from 0 to infinity, take the n and have it as a divided by z. So now we have a b, and we have this exact formula right here, and we get our z domain formula. So looking at the last example on the last page graphically, so say that the casual exponential is exponential. So with a equal to e, and if we look at the graph, we have a circle, right? So this is a regional convergence. So just a quick introduction to what the regional convergence is where everything where it's shaded is where the z transform exists, and inside the circle is where it diverges, so it doesn't exist there. More about that in the next video where we introduce regional convergence, but just a quick look at that. This is what it will look for that. And then looking it through equations, we derived this equation on the last page, but we didn't mention this part. So the identity also comes with b needs to be less than 1. So we get this as a regional convergence. So you can see that the boundary is most likely a. So relating z transform to discrete time Fourier transform. So say we get this general equation and we had a circle on the last slide, right? So the circle can be described with a polar form where z is a polar form. So if we come back to this slide, we can relate z transform by making z equal to a polar form, right? So if we let that happen, and r would be the radius of the circle and e to the power of jw is the frequency component, we input that into the general equation, we get this formula, right? And if we look at this formula, we can definitely relate that to the DTFT. So if we look at the DTFT equation, we get this equation, right? And what we derived on the last slide would be this equation. The only real difference is this part right here, right? So we have to get rid of this radius of the circle, right? And what we can do with that is make r equal to 1. So r to the power of anything is always 1. So once we do that, these equations are identical and they give us the DTFT. So it'll be the unit circle because the unit circle's radius is always 1. So if we compare this to graphs, if we look at this 3D graph, you have this magnitude graph right here, or magnitude axis right here, and you have a real axis here, and you have an imaginary axis here. So we looked at the circle in the last few slides, but we didn't look at the magnitude part. So at each point of the circle, there is an angle and there's a magnitude. So the angle would be from the origin to the circle, it's a boundary, and then there should be a magnitude there. So if we break that up and we cut this magnitude in half, we get, and it's a unit circle, so we can get the DTFT signal right here. So if we cut this in half and put it on vertically like this, and we change the axis to the angle, because we're looking at angles here, we get the DTFT magnitude spectrum, and this should have a 2 pi periodicity, just like we saw in the third slide. And that circle also confirms the periodicity as 2 pi because the circle is, so you start from 0, you go around 2 pi, and then if you get to 3 pi, that should equal to the same magnitude as pi, so it just repeats every 2 pi. And yeah, circle equals 2 pi periodicity.